Hello, today we continue with the chapter 4 on forces. We will learn how we draw our forces because this is what we went through yesterday. Today we will do it in a clearer way, in a more clear way. So let's assume we have these objects, okay? Let's assume we have these objects number 1, 2, 3, 4, until number 10. And the question is asking me to draw the forces acting on each of these objects, okay? As a reminder from yesterday, these are the 4 forces we will be dealing with primarily for the rest of this chapter. Of course, if there are other forces, the question will illustrate that for us. But usually, normally with this chapter, we will be mostly dealing with weight, normal, tension, and friction, okay? If there is a tracking force or any other force, that will be mentioned in the question itself. So weight, we said it is always perpendicular to the ground and toward the ground, okay? So it's perpendicular to the ground. So it's always downward like this. It's always perpendicular to the ground. If I have the ground here or here, okay? So I always draw the weight perpendicular to the ground, okay? Now, normal and the weight is always toward the ground, okay? So it pulls toward the ground. Normal is perpendicular to a surface. Okay, so if there is a surface, let's say here there is a surface, then the normal is perpendicular to the surface. Let's assume that the surface is a table, that this is a table over here. So the normal is perpendicular to the surface and away from the surface. So it pushes away from the surface. Okay, it doesn't attract it. It pushes away from the surface. Now, the surface doesn't always have to be horizontal. The surface can be also inclined, like a slope. So in this case, the normal is also perpendicular to the surface. And in this case, it will be like this. Okay, so it's not always vertical. It can also be having an angle, because in this case, the inclined plane is having an angle. Okay, the tension is always parallel to the string or the spring. So if I have an object, attached by a spring or a string, so let's assume it's attached by this rope, for example, or a string, the tension is along the rope. Okay, it's along it like this. Okay, so it's parallel to it. We say it's parallel to it and it's along it. Friction is parallel to the surface. So if there is a surface, let's assume there is this floor, there is a friction. So if I have an object moving in that direction, if I have an object moving in that direction, the friction is always in the opposite direction. Okay, it's always in the opposite direction. So these are the main forces we will be dealing with. Let's go back to slide 1 and draw our forces on each of them. So number 1, it's an object lies motionless on a surface. Okay, when we say draw forces, in other terms, we say draw a free body diagram. So it's called a free body diagram. Okay, so it either tells me draw forces acting on the box. This is in simple terms, but in this chapter, we will be saying draw a free body diagram. In order to draw the free body diagram, 2 things. First, draw the surface. Okay, draw the surface. This is step 1. Step 2, draw a point. Draw a point to illustrate the object. So instead of drawing the box and putting forces on it, we will put as a point and put the forces on it. Third step, it will prove useful later, but for now we will do it. Draw x-axis and y-axis. How to draw them? X-axis along motion, y-axis perpendicular to it. Okay, this part 3 will be proved important later when we discuss Newton's second law. Okay, for now we will just draw the surface and draw a point to illustrate the object, but this number 3, keep it in mind because we will get back to it later. So the first thing, I will draw the surface. So this is the surface. Okay, and I will put a point where I will put the forces on it. So this is a point where I will put the forces on it. So I have weight, normal, friction, tension. What exists here? The first force to think about is the weight, okay? Because there is always weight. This is an object that has a mass, so it has a weight. So the weight is perpendicular to the ground. So if the ground is here, perpendicular to the ground is here. Okay, this is the weight. Okay, then there is a surface. If there is a surface, then there is normal. If there is a surface, then there is normal, and it's perpendicular and away from the surface. So if this is my surface, this is my surface here. So it should be perpendicular to the surface and away from it. So the normal will be upward. Okay, I should draw them in such a way. So that is normal. Next, normal vector. Okay, it's motionless, so it's not moving. Is there any other force? Well, if there is a surface, there can also be friction, but it didn't tell me anything about the surface, if it's frictionless or smooth. So I assume there is no friction. Okay, so we drew the normal and the weight. These are the forces acting on this object. Let's move on. Just erase this. So again, draw a free body diagram. Here, draw a free body diagram. So there is a surface, so I draw the surface. And there is an object, so I will put a point, okay, as small as possible. Object slides at constant speed along a smooth, frictionless surface. So it's frictionless, okay? So what are the forces acting on this object? Again, weight always perpendicular to the ground, so downward. Then normal, because there is surface, so it's upward, making 90 degrees with the surface. It's going at constant speed, but there is nothing pushing it, so there is no more force. Okay, there's nothing pushing it, so there is no more force. So I have the normal and the weight. Normal and weight. Okay, let's move on. Object slows down due to friction. So this time there is friction as well. So surface again, a point or a sphere where the forces act on. So this is the box. Now I illustrate it with this point, and the forces are weight perpendicular to the ground always. The surface, since there is surface, then there is normal. And since there is surface, which is rough, there is friction, so there is a friction. Okay, it's along the surface. So I have weight, normal, weight, and friction. These are forces, these are vectors, so I put a vector on top of it, okay? Okay, so let's move on. Now, object slides on a smooth incline. Okay, so there is a smooth incline, smooth, whenever it says smooth, implies no friction. Okay, smooth implies no friction. So I draw the surface, and this time my surface is inclined. Okay, I put my object. Now I have the weight always. It is perpendicular to the ground. So before I continue, I draw the ground. Okay, I draw the ground. This is the ground. So as I can draw the weight perpendicular to the ground, just to make it more. So this is here the ground. Okay, now I draw the weight. It's perpendicular to the ground. You make it touch the ground. You make it touch the ground, so as later it becomes easy for you. And we have a surface here. We have a surface. So there is the normal perpendicular to the surface. Okay, so it should make 90 degrees with the surface. 90 degrees with the surface. Okay. What else? Smooth incline, so there is no friction. So I only have weight and normal vectors. Okay, let's move on. Friction on an incline prevents sliding. So I have this object on an incline and it doesn't move due to friction. So it's telling me that there is friction. Okay, so first I draw the surface. Again, I draw the surface. Okay. I will be drawing the weight perpendicular to the ground. So I draw the ground. This is the ground. Ground. And this is my object. Okay, so weight perpendicular to the ground. Okay, normal perpendicular to the surface and away from it. And in addition to that, now we have friction. It's parallel to the ground. Okay, it's along, sorry, to the surface. So this is normal. This is weight. And this is friction. And all of them are 4 vectors. Okay. Now, an object is suspended from the ceiling. So what are the forces acting here? Here, there is no surface. No surface. No surface implies no normal and no friction. Okay. No, there is no surface. So what do we have here? Okay. So we have the object. It has weight, always there is weight. So the first force you draw always is weight. And then there is a rope. Because there is a rope, it means there is tension in the rope. Okay, so this is weight and this is tension. Okay, let's move on. There is an object here that's attached to two springs. So I put the solution directly. So this is my point. There is weight perpendicular to the ground always. Then there are two springs. So there is tension 1 and tension 2. Unless it tells me they are equal tensions, then I just call them T and T. But here there is tension 1, tension 2. This object here is also attached to two springs. So the first is the weight perpendicular, always the weight, notice, perpendicular to the ground. Then there is tension 1 and tension 2. Okay, there is no surface, so there is no normal. This object, first there is surface, so we draw the surface. Okay, then there is my object, and it's attached to a rope, so I have to draw the rope. Okay, what are the forces acting on this object? First is the weight. First is the weight perpendicular to the ground. So I better draw the ground. Okay, so this is the ground. Then I draw my weight until it reaches the ground perpendicular. So this is the weight. There is a surface, so there is normal. And there is a spring, so there is tension. Okay. I hope by now you find it easy to draw that three-body diagram. I'm giving as much examples as possible. Okay. Last example, if the object is also here, the object is motionless. So this is an object that has how many? This is an object and this is a surface and this is another surface. So there are two surfaces. There is this surface and there is this surface, right? And first of all, there is, and we have the object. Let's put it here. It's between the two surfaces. Okay, it should touch. Now, the first force always is the weight and it should be perpendicular to the ground. So I have to draw the ground. This is the ground. Now for the forces. The first force always is the ground. Never forget this. Okay. Then there is the first surface, this one. So there is a normal force perpendicular to it. This is normal 1. And then there is the second surface, this one. And so there is a second normal in this direction. Okay, so this is surface 1. This is surface 2. Okay, this is weight here. This is normal 1. This is normal 2. Okay. it didn't mention anything about friction or anything, so we assume there is no friction. So this is how we draw free body diagram. Now, the only law we have in this lesson, the only law we have, it's the only formula you need to memorize, is summation of forces as vectors is equal to MA. Okay, this is called Newton's second law. So if an object is moving in a certain direction, in a certain way, in a certain fashion, it will move in such a way the forces acting on it will affect its motion. So notice how the forces affect the acceleration. Okay, so whatever forces I have, it will affect how the object will be moving. And this is why yesterday I said, why the object will go upward, why the object will go downward, why it will stop after some time. Why? Because of these forces acting on this object. Okay, now if we look on this equation, which is a circle, we have F vector equal to MA vector. How do we deal with such formula? This is summation of vectors. In order to work with a formula with summation of vectors, I have to divide it into summation of Fx, summation of Fy. Okay, summation of Fx will be MAX, summation of Fy will be MAY. Okay, now hint, always choose x-axis along the motion. If you choose the x-axis along the motion, AX becomes A. Okay, AX becomes A, and AY becomes 0 because the motion is along the x-axis. So the acceleration, so if the object is moving in this way, okay, if the object is moving in this way, choose the acceleration, choose motion along this, choose the x-axis along this way. So choose the x-axis along this way. Then, if now I draw the acceleration, it's along this way as well, which means it only has an x component. It doesn't have a y component. So it only has an x component equal to A. It doesn't have a y component. Now, if I look at my two equations, summation of Fx will be MA, and summation of Fy will be 0. Okay, so I facilitate my life. Now, let's see how do we apply this. Before I start solving any problem using Newton's second law, the first thing I do is I draw free body diagram. And I hope by now we know how to draw free body diagram. The second thing we do is we choose x-axis along motion. So no matter how the object is moving, you choose the x-axis along motion. Then the y-axis will be perpendicular to the x-axis, okay? So the y-axis is always perpendicular. You choose the x-axis, then you choose the y-axis perpendicular to it. Then you apply these two formulas, summation of Fx equal MA, summation of Fy equal to 0, okay? Let's apply this to this simple example here. So there is this sled, مزلاج يعني, is tied to a tree on a frictionless, so there is no friction, snow-covered hill. The sled weighs 77 Newtons. So what is this? This is weight equal 77 Newtons. This is weight as a magnitude, okay? This is weight as a magnitude. The first question is draw a free body diagram. Here I'm putting Newton's second law. Draw a free body diagram for the sled. So just as we did before, we have to draw our surface. We have to draw the ground because here the surface and the ground are not the same. So this is the surface. No need to write it. We know it. This is here, the ground. Okay, and we have to draw the forces. So the first force is the weight. Let's do it in another color. You draw it until it touches here, okay? This is the first force. And then the second force is the normal because I have the surface. So this is the normal because I have a surface. It's perpendicular to the surface. And what also I have? I also have this rope. So I also have tension. Okay. And I'm drawing these on this here. So let's name them. I have normal. I have tension. And I have weight. They are all vectors. Okay. What else is given? What else is given is that this angle is 30 degrees. Okay. If I have this angle 30 degrees, implies I have this angle also. Before I go to that, before I go on, so draw a free body diagram for the sled. This is the free body diagram for the sled. Okay. Now find the magnitude and find the magnitude of the tension exerted by the rope on the sled. So we said the first step is, whenever I have a question like this, the first step is draw free body diagram. So even if he doesn't ask me to draw free body diagram, I have to draw it. Okay. Then I have to choose, let's go back to the previous slide. Then we choose x-axis along motion, y-axis perpendicular to it. Here there is no motion. When there is no motion, we are free to choose the x-axis. Here, if it will move, how will it move? It will either move downward or upward, right? But it's standing still. So I'm free to choose x-axis either upward or downward. It wouldn't cause any difference because anyway, it's not moving. So I will choose the x-axis in this way. Now I choose the y-axis perpendicular to it. So y-axis is perpendicular to it. So let's put this here on our free body diagram. I'm gonna put it in a different color. So the x-axis will be in this way because anyway it's not moving, and the y-axis. Okay, so this will be, sorry. This will be the x-axis. Okay, and this will be the y-axis perpendicular to it. Okay, so this is x-axis. This is before I can try to solve anything. Now, what are my two formulas? My two formulas are summation. I have to write it as summation of fx is equal to ma. But how much is the acceleration? Acceleration is 0 because the object is not moving. So this is equal to 0. Okay. And summation of fy is also equal to 0. Now, in part B, what does he want me to calculate? Find the magnitude of the tension exerted by the rope. So he wants me to calculate the tension. I come to my free body diagram. Okay. The tension, on which axis is it? On the x-axis or on the y-axis? It is on the x-axis. So which equation I have to use? Summation of fx equal to 0 or summation of fy equal to 0? I have to use summation of fx equal to 0. Now, what are the x? I have three forces. So I have nx plus wx plus tx is equal to 0. Remember, this is the summation of vectors algebraically. So summation of fx equal to 0. This means n, the x component of n plus the x component of w plus the x component of t is equal to 0. Now, what is the x component of n? So this is n vector. All of it is on the y-axis. So what is its x component? It does not have any x component. Plus, what is the x component of w? This one I have to draw. X component of w. How do I go to w? To go to w, this is the x-axis. So first I go, let's change the color. First I go this way, right? Then I go this way. Let's elongate it a little bit more. So first I go this way, then I go this way, perpendicular to it. Right, so this is the wx. And this one here is wy. Is it clear? Where's the wy? I'm trying. So wy. So this is wx and this is wy. Now, how to calculate this wx? I have, if you look at this triangle, let's call it OAB. Let's call it, okay, I don't want to. Let's call this triangle O. A, B. OAB. If this angle here is 30 degrees, then how much is this angle over here? This angle, how much will this angle be? If this angle is 30 and this angle is 90, we know it's 90 because it's perpendicular to the ground. So if this is 30, how much is this angle? It is 60. It is 60, okay? And WX, this is a right triangle, and I have W, it's 77, and it's making 60 degrees, okay? This WX is adjacent to the 60 degrees, right? So WX is how much? It is W cosine angle theta, which is 60 degrees, plus TX. How much is TX? Sorry, WX, we just have to pay attention that it is in the negative direction. It's in the negative direction, so it is minus cosine theta, okay? Plus now, vector it's TX is along the x-axis, so TX is T, but is it a plus or minus? It's a plus because it's along the positive x-axis, so I leave it as plus, okay? This is equal to 0. Now I solve. Minus W, which is 77, times cosine theta, it's 60, it's the angle up there, plus tension is equal to 0. This gives me tension equal 77 cosine 60, which is equal to 38.5. Okay, Newton. Okay, this is part B. Part C, it's asking for the normal. Okay, now it's asking for the normal force. Normal force is along y-axis, So I have to use summation of y of fy equal to 0. Now, what forces are on the y-axis? There is the vector n. So now I will say ny plus wy plus ty is equal to 0. Okay, ny is all of n. Ny is all of n because it is along the y-axis, plus wy is this thing over here. If wx is w cosine 60, so wy will be what? Notice this angle, it's opposite to wy. The opposite of this angle is wy, so it should be w sine theta, but pay attention that it's in the negative direction of the y-axis. Okay, so it's minus. T is along the x-axis, so ty is 0. So this is 0 is equal to 0. Now I just plug the numbers. So n will be equal to w, which is 77, times sine theta, which is 60. This is equal to 77 sine 60. This is equal 66.7 degrees. Sorry. Okay. So this is a small exercise how we applied Newton's second law. There was this difficulty with the triangle and the angle over here. Okay, so I still have some time before the screen, before Zoom stops. So I'm gonna repeat for you how we draw this free body diagram and how I chose the angle and how we got that wx and wy are w cosine theta and w sine theta. So let me repeat this. I'll repeat everything here. Okay, we will make it bigger, so I'll put more information. So to draw the free body diagram, the first thing we do is we draw the surface. So we draw the surface. Let's make it a big surface. Because we have to draw the weight, so we need to draw also the ground. We also need to draw the ground. Okay. So this is the ground. Now, our object is here. Let's put it on top here. And it is attached by a rope. It's attached by a rope. Let's put the forces acting on it. We always start by the weight. Let's choose another color. So we start by the weight. It's perpendicular to the ground. Okay. Then the normal, it's perpendicular to the surface. Then the tension along the rope because there is a rope. Okay. Now we name them. We have W. We have normal. And we have tension. Okay. They are vectors. So I draw vectors on top of each one. This is the free body diagram. Now, before I continue, I choose the x-axis and the y-axis. The way I chose it is like this. This is the x. Let me change the color. I'll choose this to be the x-axis. I can choose it either going up or going down. It doesn't matter because the object is not moving. But if it moves, it will move along this line here. If it moves, it will move along this line here. That's why I chose the x-axis like this. Now, if I choose the x-axis like this, the y-axis will be perpendicular to it, like this. Okay. Now, this is x-axis. This is y-axis. Okay. Now, The first part, find the magnitude of the tension exerted by the rope. We looked at the tension force is along, so the tension vector is along the x-axis, implies I have to use the first formula, which is summation of Fx equal to ma, but the object is at rest. Because the object is at rest, so the object is at rest implies A equals 0. This is why we took A here to be 0. Here, okay? Now, I have three forces, so I have an x plus wx plus tx is equal to 0. Now, what is an x? I look at vector n. It is always along the y. Actually, you can memorize this. Normal is always along the y because it's always perpendicular to the surface. So the y component of n is 0. Okay. Now, what is the x component of w? This is vector w, the one going downward. How to draw its x component? Let's choose a different color. I find the tip of it. So this is the tip of it. Now, I go on the x-axis until I reach the tip of it, right? Then I go along the y-axis until I reach the tip of it. Here we go. So this is wx. And this is wy. Okay. Now, how to find wx and wy? I have this angle theta here. I have this angle theta here, 30 degrees. 30 degrees. It's 30 degrees. Now, look at this triangle. I named it O just to make it easier for you. O, A, B. Okay. If you look at this triangle OAB, if this angle is 30, then how much is this angle over here? This is a right triangle right at A. If this angle is 30 and this angle is 90, then this angle is 60. Okay. WX is adjacent to the 60. So WX is W cosine theta. Okay. WY is opposite to 60. So WY is W sine theta, where theta is 60 in this case. This is 60. So now we found that this angle over here is 60. Okay. I just have to pay attention that WX is in the negative x-axis and WY is along the negative y-axis. Okay. So I come here, instead of WX, I put minus W cosine 60. And TX is T because all of T is along the x-axis. Instead of W, it's given 77 cosine 60 plus T equal to 0. I get the tension. For the normal, I have to do the same thing, but along the y-axis. So summation of Fy equal to 0, Ny plus Wy plus Ty equal to 0, and minus W sine theta equal to 0. So N equals 77 sine 60, and this is equal to 66.7. Okay. I hope now it's clearer as I'm repeating it for the second time. So this is Newton's second law. This is what we will be dealing with. Summary. In each problem, the first thing we will do, draw free body diagram. The second thing we do, choose x-axis along motion, y-axis perpendicular to it, apply the formula, summation of Fx equal ma, summation of Fy equal to 0. If the object is at rest or moving with a constant speed implies implies acceleration is equal to 0. Okay, then this becomes summation of fx equal to 0, summation of fy equal to 0. Some people like to call this Newton's first law. And the one with MA not equal 0 is Newton's second law, but to me they look the same. It's just that one with 0, one without a 0. So we don't have to call it Newton's first law. You can just use it Newton's second law and you put instead of A equal to 0. Okay, I hope you found this lecture easy. Please don't hesitate to send me any question to my email if you have any questions in this regard. Okay, so that's it for today's lecture, and tomorrow we solve more exercises.